Ladies and gentlemen, welcome to the Royal Swedish Academy of Engineering Sciences, EVA. All of you who are here with us today in the Wallenberg Hall in Stockholm, and also all of you who are following us online. My name is Tuula Teeri and I'm the president of EVA. I'm very, very happy to see so many international guests here in Stockholm today. Back in 2019, we had an American delegation from NAE before, and we had participation of a large delegation of young scientists in a EU-US conference, which is called Frontiers of Engineering. We organized that together with National Academy of Engineering, and today we also organized this conference with the National Academy of Engineering, which is a great pleasure for us. Back in 2019, we were talking about 5G and Internet of Things, and things are moving very fast in this area. So now we are going to be discussing the development of 6G, and who knows, maybe next year, further on. EVA was founded 100 years ago in 1919, and that was because there was a need in Sweden to have science-based, technology-based advice in the middle of an energy crisis and also industrialization of Sweden. And ever since those days, we actually have been a meeting place for scientists and industries and private sector, public sector, working together to support policymakers with technology foresight and policy advice. So as you may know, Sweden is quite a small country, but we're very innovative. And for years in Europe, we have already been kind of continuously ranked as #1 innovation country. Of course, as you know, competition is hardening, so we have to work very hard to maintain that position. But this year we actually gave out a book on 50 Swedish innovations over times that the Swedish government actually handed out to our European guests during the Swedish presidency of the Council of the European Commission. And our American guests will tomorrow have copies of this book available for you to take home before your departure. It's quite an interesting read. One of the innovations is, for instance, paternal leave for fathers of children. So there are some surprises in the book. One of the flagships along our innovation history is really telecommunication. You will find many examples also of that kind of innovations, such as mobile broadband and 3G in this book of innovation, the Swedish way, as we call it. And one of the success factors in this book and in Sweden in general is that we have good infrastructure for communication. We're also a small country, so we know each other quite well, and it's easy to find each other. But still, by the end of the 19th century, Sweden was the country that had most phones per capita. I think it kind of reflects this desire that we want to talk to each other. And 100 years later, 1994, the Swedish Prime Minister was the first one to send an email to the US President Bill Clinton. So we have really embraced these kind of mobile technologies and telecommunications. And the thing is that, as we know, the importance of new technology and engineering solutions, the need for them is growing in the light of the grand challenges that the world is facing today. And that's where we come also to collaboration. When the challenges are growing, we have to actually join forces to tackle them. Otherwise, we will not able to do it fast enough, at least. And collaborations between academic and business communities and policymakers will be really essential, and not only within countries, but of course across nations. So we take great pride in serving as a bridge builder between academia, business and policy, and that in this wonderful international setting today, as we see in this room today. And it's now my pleasure to introduce a co-host and the first speaker, not only the group CTO Ericsson, also a fellow EVA and a vice chair of our presidium, Ericsson. Welcome. Ekudden, kom. Välkommen.
Thank you. Thank you, Tuula. And thanks also, of course, to Eva for hosting this. Before I start, I'd like to bring up a distinguished guest and clearly one person that has made this happen. And Alpisano, could you join me here? Just say a few words. You are the engineering dean of UCSD and also the founding chair of the NAE Dean's Roundtable. So
yes.
Great to have you here.
Thank
Welcome.
you, Eric. Thank you. So, ladies and gentlemen, I'm very honored to be asked to represent John Anderson and Al Romig, the president and the executive director of the American NAE here. They regret that they can neither attend nor come in later via streaming because there's some sort of important federal meeting they have to go to, and they've been vacuumed up into that. So I just want to offer that, yes, I am pleased to be the founding chair of the Dean's Roundtable. Nothing related to the Knights of the Round Table. Jousting has been forbidden, but when you put American Deans at a round table, they joust anyway. All right, but to be serious for just 30 seconds, the NAE is pleased to be teaming with Eva on this important topic. John Anderson himself communicated to me that now is the time for the engineering societies, the engineering the engineering academies to step up and take a leadership role. They play an extremely important neutral ground, a level playing field, a place of discussion and collaboration that few organizations around the world can fulfill. And in each major country, there is an Academy of Engineering. So we will have other presidents make comments at the end of the session today. The point is we hope to see that number increase, and through them we hope to see yet another set of ligatures among the countries be tied together. So thank you very, very much for the opportunity to address you. Good day.
Thank you. Thank you, Al. So why this interest now in something that's going to happen 2030 or beyond? Wireless technologies. Well, I'll share with you a few of the things that are happening in today's wireless industry and 5G and 5G advanced. But I'll also touch upon why it's so important to think long-term here, think about what we can do for 2030 and beyond. So let's see here. Supporting me with this, I have a few stats. And let's start directly with where we are with 5G. Many of you know this because you're experiencing it every day. But if you focus on where we are right now, left-hand side, we have really rolled out 5G more or less around the world. 239 live networks globally. And about 1 billion 5G subscriptions already end of last year. So it's taking off, phenomenal rollout speed, and it's also used for new applications, not just your smartphone, but actually reaching the residential market. So you're more likely to use broadband with 5G rather than fiber in some markets. And this is, of course, a new business opportunity now when the technology is able to do it. To the right here, you see that over the coming 5 years until 2028, we expect that we will have about 4 times, 3.9 times as much traffic, mobile traffic across the world's network. And part of that is going to be on legacy technologies, 2G, 3G, 4G. But about double that, 1.9 times today's total traffic will be 5G traffic. So it's really taking over really rapidly. And about the same amount of traffic in the purple part here will actually be traffic using mobile technologies to homes, residential traffic. So it's growing at a phenomenal speed. Of course, we all know that watching video or Netflix on a large screen consumes a lot more data. So there is no denying that this would put a lot of strains on the networks. It could be 10 times, 20 times, even 30 times as much traffic per subscription or per session than you would normally have in a mobile broadband situation. So networks will be strained beyond 2028. But it's not just what we see as consumers and homeowners or getting access to residential. It's also very much about this technology being the digital infrastructure being the technology of choice to connect smart manufacturing, smart education, smart health, all of these things that been sizing to the left here in terms of a really, really big market already by 2030. And in the middle here, you see actually, which is an ABI research graph, that if we go a few years into the future, beyond 23, 24, we expect a mass adoption of wireless also in smart manufacture, also in the manufacturing space. And why is that? It's simply because the technology is so powerful that you don't need cabling in a manufacturing site. You get the flexibility, and compared to alternative technologies, you get a much more secure, reliable service when you go wireless. So that is actually a very big part of the transformation towards Industry 4.0 for real. Digital infrastructure powered by 5G technology, of course a lot of AI and edge compute and many other application developments on top of it. But it really starts with building it on top of 5G. But there's other things. Of course, it feels a little bit pricey when you have to pay $3,500 for your next goggles or the AR glasses that were launched just a few days ago. But I'm actually very convinced that it's the future. And it's the right thing for many industrial applications, many enterprise applications, augmented reality glasses. But over time, what will happen is that these glasses will be much more lightweight. They will come down in price. They will have much of the compute done not on your glasses. To get to 50-gram glasses, you need to move much of that compute into the network edge. But you can see this happening over, let's say, a 10-year period, where today you can already start to get blended information in a head-up display. Give it another 4 or 5 years, and you will be able to have augmented reality recognizing the surrounding and creating geo-specific experiences. And that would, of course, be clearly you can carry it a full day. That's kind of the 2025, 26 perspective. And you go out to 2030 and beyond, then it's a fully immersive experience. How do we take care of that? How do we make sure that networks and infrastructure can really handle this kind of traffic type? Well, coming from the network industry, we know that we have to take care about performance, and in the coming 5 to 10 years, it's going to be new constraints or new requirements on networks in terms of uplink capability, in terms of capacity, and also bounded latencies. Today's networks, they are really, really good at passing data. But when it comes to honoring an SLA, when it comes to a latency requirement, not so much. It does vary too much for some of these applications. If you want to move some of the processing from the glasses into the network, latency and bounded latency will be critically important. So from our point of view, this could be the next paradigm when it comes to user experience and user interfaces. So the next phone or next device after the smartphone. We look at this very much as an ecosystem build, something that will happen over the coming 5, 10, 15 years as a collaborative effort. Of course, there's standards. Of course, there's partnerships. There's a lot that needs to happen in terms of enabling this future or meet the future needs that I mentioned. And some of that is starting in this room. Some of this is about putting stakes in the ground when it comes to new technology that can help us in these areas. But some of it, I think, is a big change in the whole ecosystem when we're going from consumers into enterprises, industries, residential I already mentioned, and of course everything that happens in society at large. So that's why the openness, the way to build systems in a much more open way than today, programmable infrastructure, meeting SLAs that are much more stringent than today, having networks that are focusing on performance and differentiated performance will be critically important. There is no way that we can support all these new needs and new use cases unless we allow for differentiation. Some applications need much less requirements from their infrastructure, others need much more. And this kind of flexibility is really what we have to build in from day one now over the coming 10 years. But, of course, this is a journey that will have multiple steps. So this is not about what we do now versus what we do 10 years into the future. We will see a lot of these capabilities being integrated into the digital infrastructure in steps, starting already this year when it comes to more advanced 5G services and more advanced resource reservation services, such as with network slicing as the technology is known. So this is happening, but it's going to be, again, a stepwise multi-year journey, and the horizontalization of network, the cloudification of network, what we're doing on the openness across the network infrastructure, those are key pillars in this journey, and they start already now. So if we then allow us kind of looking into, let's say, 2030 or beyond, what is it really that your technology, the technology that we will work on and invent over the coming 10 years, what can it give us? Well, I'm more bullish after having seen some of this firsthand that we'll have to cover much more of a range of capabilities, from the zero energy harvesting sensors, perhaps in your clothes, a few bits per second. But it's important data and it needs to get through, but it's not a lot of data, all the way up to the 100 gigabit per second that some applications will require, and certainly the infrastructure itself need to handle these kind of bit rates. So what we showed was these energy harvesting zero energy IoT devices, and we showed it in the form of a sweater, a knitted sweater, in Barcelona earlier this year, in Mobile World Congress. And of course, this is early research. This we are proudly presenting as work from MIT. We see that a lot of new innovation will come from just stretching our imagination in terms of requirement space. And again, this is perhaps one of the simplest things. How do we go from super low bit rates to the very, very high bit rates? But think of all the other things that I touched upon, to be able to be adaptive to applications and needs and the enterprise space. You will have so many more resilience requirements that we can't handle today. You will have so many more requirements in terms of latency, energy, security, and so forth. All of that, of course, is sort of a great opportunity to innovate going forward. We look at this very much as a journey towards digital and physical meeting, a cyber-physical system, or perhaps a cyber-physical continuum. And now I'm not going to go through and show you these videos in the middle here. I think we can look at them afterwards if there's an interest. But what it really helps us to do is to find some of the real requirements, find some of the real critical points. What do we need to solve for by 2030? How do you make cities safe? How can buses and pedestrians and bicycles, how can they communicate in a very integrated way, avoiding accidents? How can we make sure that the infrastructure is able to inform us much more about what happens around us so we can make informed decisions? And of course, ultimately, machines that have much higher needs than humans in terms of communication, could be in terms of certainty, latency, and other parameters. That, of course, opens up for requirements way beyond what we're doing today. But it all comes back also to the importance of energy efficiency. So to break the energy curve, making sure that energy efficiency is at the forefront of the research that we're doing. Energy consumption in networks, energy consumption in the combined devices, sensors, and the networks need to go down significantly. We're talking about meeting the Paris Agreement, but I think we are not bold enough. I think we can accelerate that by years by introducing digital technologies much, much faster. In fact, our own research shows that by just introducing today's digital technologies, we can actually reduce CO2 emissions by as much as 15 to 20% of global levels already by 2030. And I think we can be even bolder, certainly going beyond 2030 on that. So very much about this limitless connectivity everywhere with satellites, indoor systems, all the terrestrial systems, security and privacy coming forefront, the automation and AI-driven cognitive networks, and of course, bringing compute, storage, and networking together. Sometimes we think of it as a natural fabric because we are kind of used to not think so much about the network. But 10 years from now, I think we will all be much more aware about the networking part, very much complementing the compute and the storage part. And that's where this has to not just come together in a cloud-based open architecture, it also will be much more of a driver for innovation, because then we're not separating the needs of applications from how you build and monetize networks. Then we start to connect the needs of applications with the investment that needs to happen on the digital infrastructure. So we are sort of closing this gap. Applications not understanding networks being black boxes, networks not understanding what applications needs. We need to close that gap, and that is something that we can really do over the coming years by focusing on some of these areas. So with that, I'm just going to sort of a call out or a shout out in terms of the real purpose of having this seminar from our perspective. This is a journey which is not about technology as much as it's a journey about talent. It's really about collaboration. I think it's a great start what we can do between the two engineering societies or academies. But I think much more on individual level. I think we need, as representatives of the networking industry, we need much more talent over the coming 10 years. We need many more with engineering degrees. We need many more interested in making this not just a great innovation platform for societies to digitalize, but also a great career, a great place to really do good and ultimately advance the technology. Because what we are showing here is no simple thing. I think we are stretching ourselves and the imagination quite a lot. I think this will require to have an increased number of engineers in, of course, the areas that are closer to networking, wireless technology in particular, but I would say networking. Of course, AI comes into this. Of course, any kind of advanced compute infrastructures, whether it be in quantum compute or neuromorphic or other genres, all of that, of course, needs to come together. Otherwise, I think that we will have a tough time to meet these needs of, let's say, 2030 and beyond. But it's a good start, what we're doing here, because I'm very confident that these cross-border, these international collaborations, especially now between US and Sweden, they will really pave the way for kind of not just reinventing this industry, but changing society for the better. So these are just a few examples, of course, your own universities. We are also very convinced that this needs to go broader than Sweden and US, but we are very happy that we could take this opportunity to start to form alliances and perhaps start new projects in light of, or in the direction of what I showed earlier, meaning that networks and the connection to the societal needs, not just sustainability, not just consumers and enterprises, but the broad needs. That's really the journey that we are hoping for, and I think this is a good start. So with that, big thanks, and I'm going to hand over to the next speaker. Thank you. How you doing?
Thank you very much, Erik. I think, when I listen to you, Zoom feels so yesterday. And I'm wondering, in the mornings if I'm going to have to charge my dress when I go to work. Is that the consequence of your talk? Probably. Energy harvesting. Okay, good. We think we can probably have one or two questions if you have any. We have time for that. If there's some urgent question, otherwise you can ask them later as well. All right. If not, very exciting. I think that this seminar is getting even more exciting with the next speaker, who is Dr. Tom Richardson, Vice President of Engineering at Qualcomm, and I think we will probably get more visions of the future with you as well. You're so welcome.
Thank you very much. Okay. So the bottom button advances.
The green one in the middle. Yes.
The green one, okay. So thank you very much for the invitation, opportunity to present to you a little bit of Qualcomm's view of the transition 5G to 6G. So yeah, what I'm going to present is a little bit of a sort of broad view of how Qualcomm views the transition into 6G and what's happening in 5G, and then dig in a little bit to a couple of the applications which are currently driving this transition and what's happening from our perspective. Okay, so if the 3G to 4G transition was about taking the internet fully mobile, a big part of the 4G to 5G transition was about enabling digitization of new verticals. And at the time, I remember at the beginning of the 5G discussions, the ones that were talked about the most were autonomous driving and remote medical procedures. Neither of those have, of course, we now have C V to X in the automotive space, and they're both evolving, but I don't think that these are the ones that are currently driving, what the standards towards what 6G will look like. So industrial IoT is much more central, and actually AR, I think, is the other one I want to talk about a bit later. But we expect these industries to all to grow and to create enormous value into the future. Okay. Okay, so the transition from 5G to 6G, from the Qualcomm perspective, it's going to be driven mostly by sort of the movement of AI from the cloud into what we call the connected intelligent edge. So this involves mainly the convergence of wireless, which is Qualcomm's bread and butter, but as we've already heard, integrating computing and distributed AI into the system is going to be the definition of 6G, and we call it this from the cloud inward, the connected intelligent edge, and Qualcomm in particular is trying to play in all these spaces now, moving beyond just being a wireless company. And we expect these systems in the future to create new applications and better networks supporting better privacy, reliability, latency, of course, and efficiency. Okay, so where we are right now, we're in the second wave of releases in 5G. So release 18 is what's happening right now. And I'm going to talk about some of the things that are happening in release 18. And we're starting to see, just as we did in 4G, what maybe was missing in the initial foundation and how we want to move it forward into 6G. So 6G itself, the expectation is that the first study group will start around 2025, and around 2027, the actual work will begin. So we don't really know yet exactly what will be in there. Of course, companies are working on the ideas that they want to contribute. As 5G advances, we'll see better. And you can see this in some of the applications. Okay, so what's happening right now in 5G in release 18 is we're already seeing AI being brought in. So there's already standardization of interfaces between nodes in the network. To support higher bands, we're seeing a change in the deployment structure. So things like mobile IAB, integrated access and backhaul, and also smart repeaters. Duplexing is also important change to the air interface because it enables much lower latency and important, for example, for real-time control. So on the other side, we see that we're also starting to see new devices come in. And so as mentioned already, AR, so we also agree that this is probably an important change in the nature of what the network needs to support. So we see, besides AR, we have a whole range of new devices and things like expanded side-link. So side-link began in 4G, morphed into CV2X, and now it's kind of morphing back into many other applications. So the network structure is changing, and we're including new capabilities. And positioning is also starting to play a much more important role. Okay, so where we see 6G. So 6G, we sort of see as kind of the merging of the digital, virtual, and physical world. And all these, in order for this to happen, a lot of technology developments need to occur. So one thing is spectrum. Spectrum is key to any wireless system. We're going to need a lot more of it. So people are talking about the upper mid-band, like 7 to 15 gigahertz and sub-terahertz for the next generation. This will give us a lot of additional bandwidth to work with, and also because of its nature being in higher frequencies requires a lot more understanding of spatial computing for managing the network. Disaggregation, virtualization is important for heterogeneous topology and also keeping costs down. Resiliency has been mentioned. Of course, we need additional improvements on the air interface, better MIMO, so on. And driving it all is this idea that the 6G system will have data-driven models built in and will optimize everything locally, both for context and application. Okay, so we'll move on. And this will bring us eventually, sort of futuristic types of applications like boundless XR, 3D telepresence, interacting robot systems, critical services, things like this. Okay, so how do we get there? So 5G had 3 cornerstones. So massive IoT was one, enhancing mobile broadband was the second, and the third was ultra-reliable low latency or mission-critical services. So these are all expanding. We're going to need more of all of them. So mission-critical will expand to real-time control. That's already showing up in industrial IoT, for example. But we also have these other dimensions, new vertices. So spatial perception, the integration of sensing and spatial awareness is going to be fundamental to 6G. Immersive platforms, so we're going to have new kinds of devices and environments where people interact with the network. And so this is, we consider this another fundamental aspect to the evolution. And of course, energy efficiency and societal sustainability, these are also critical. So in addition to the basic communication capabilities of the network, we're going to have these new capabilities. So AI and compute will be inherent system. Integrated sensing will be another aspect, energy efficiency and system resiliency. And each of these areas will bring with it a new set of requirements and new ways of characterizing performance. And this will be integrated into one big system. And different applications will take different cross-sections of these requirements in order to define their needs. And it's up to the system to provide optimal solutions. Okay, so 6G as a system will have to integrate all these different kinds of requirements and be smart enough to manage resources and provide the optimal performance for the various applications in different contexts. Okay, so now I'd like to spend some time and go into one of the driving applications that we see. This is AR and VR. So as always, okay. So right now we have two basic categories, augmented reality and virtual reality. So virtual reality is the fully immersed version, and augmented reality is sort of mixed reality or overlaying of digital information on the physical world. And the AR/VR platform, we expect to sort of penetrate almost all of the important applications that were mentioned earlier. So it's sort of a fundamental one, and applications ranging from fitness to education and consumer uses, and enterprise uses. So Qualcomm has a reference design for AR, and I'm showing you here the latest generation. And the way it's architected is that the glasses are connected by Wi-Fi to the phone, and the phone gives you the 5G link back to the network or back to the edge service. And okay, so where we are now is you can actually buy an earlier version of this. It's already available in the market, but a wired version. And on the top, we have this standalone VR type systems like the Vision Pro. So where we see this going is the new reference platform will carry us for the next 4 to 5 years through the AR world. And so we expect that this form factor will be important for AR traction in actual applications. At the same time, we expect the standalone versions to switch from Wi-Fi to 5G, mainly to support highly dense deployments of VR. And eventually these things will merge into, again, what we imagine to be the next fundamental computing platform, which is these sort of natural-looking glasses. And that will then set the stage for the 6G world, 6G metaverse. Okay. So I want to talk a little bit about the actual technology that goes into this. And fundamentally, for this kind of device, the key problem is you have to do distributed computation. You cannot afford to do all the computation on the device. Some of it has to be done on the edge. But a certain amount will be, of course, done on the device. So here we have a basic architecture showing the perception algorithms. So things like gesture recognition, face recognition, eye tracking, and so on, and tracking the pose of the headset of the glasses. It could be done on device. Then the processing, the results of the processing will be forwarded to the network, and the network would do the rendering, and then the frames are sent back to the glasses. So this is the basic architecture that we have in mind. And what's critical is, of course, the latency, not just the average latency, but the worst case. Okay, so I just want to show you a few examples of some of the innovations that are being brought now to the platform. So one of them is the ability to switch the rendering from the device to the cloud. So depending on the quality of the link, you might prefer to do the rendering in the cloud or on the device. Generally speaking, you would prefer in the cloud because the GPUs are much better there and you can get better graphics results. So if you have the capacity, you might prefer the top. But sometimes the link might not be in as sufficiently good state to support the required throughput, in which case, you might switch to doing the rendering on the handset. So the application, and the network has to respect the needs of the application to be able to switch between these two. Okay. So another, let's say, optimization that's being done now is to take spatial information coming from the headset and use it over the wireless link. So that the link between the headset and the handset will be optimized by taking advantage of the sensory information coming from the headset to manage the RF. In addition, we want to do some optimizations, basic optimization on the packet handling across the stack in the whole device in order to try to get the latency down. Okay, a second example is, depending on the quality of the link, you might want to change the quality of the rendering. So by adapting the rate of the image, you can ensure a good seamless experience. And I'll show you a demo in a second that we showed in Mobile World Congress last year. Okay, so this is actually from 2021, a demo. So what it shows is a user on the edge of a cell, and the gene will be there. And as you can see, the head is moving around, so there's pitch and yaw of the device. Meanwhile, that's being spatially tracked in order to manage the beam to the device. And this is all being done so as to keep the round trip latency down. And the curves are just showing that by using some of these optimizations, you can actually get the latency tails down to a sufficient level to get good user experience. So the second example was from last year, and this is showing just the advantage of adaptive rate. So this is a particular game, and it's just showing the implementation on the right with the optimizations and on the left without. And what happens is when the network becomes poor, the application stutters. And by controlling in a smart way the resolution of the video, you can create a much better user experience on the right. Okay. So where we want to go eventually is to a set of glasses that could connect by Wi-Fi, or it could go directly by 5G to the network. Now, in that case, all of the optimizations I just mentioned would have to move into the network and be supported there. So right now, developers can access the optimization through a modem APIs on the device, but eventually it's going to have to move to the network. And what's happening now in Release 18 is some additional enhancements. And I think these actually have much more of a 6G flavor, because what they're about is trying to make the network aware of the application and adapt the way it functions to serve the application better. So just quickly, some examples. So the duty cycle of the network can be adapted to the duty cycle of the application. So in particular, we can arrange the duty cycle transmission cycles of the 5G network to align with the frame rate of the application. And this can save a lot of power on the device. Another example is just making the network aware of what the real quality of service metric should be. It's not packet error loss, it's frame loss. So just being able to redefine QoS to make it fit better into the application. Another example is allowing the network to organize packet order so as to make the delivery of the traffic in a multi-user case much more efficient. So these are changes that are going to be required in the standard, but as I said, it has kind of a 6G flavor, because what it's about is the network becoming aware of the application and adapting its behavior. Okay, so eventually, of course, we want this to get to the point where we can support 3D interactive experiences and have fully immersive digital twins and so on. To get there, we're going to need much higher throughput. We need more bandwidth. We're a long way from there now, but this is the eventual goal. And so the way we see 6G in this context is a smart system that's able to adapt to the application, redistribute computational load, incorporate end-to-end QoS for the application, manage all of those resources in an optimal way in various settings, whether it's industrial setting or a home setting or an external one. Okay. So yeah, I'm going to spend a little bit of time on industrial IoT. So industrial IoT, we expect to be a sizable fraction of the market that's going to emerge from 5G. And in Qualcomm, we've been partnering with a number of companies who do this kind of integration work on factories. And we're developing a system of sort of private networks for the factory floor. And this includes things like managing the robots, real-time control, inventory monitoring, safety monitoring, and analytics. Okay, so I want to give you some examples of improvements that have been made in the air interface to support this. So this example is it's showing you an example of a robot doing a sorting operation. And the key point is that the underlying network has been synchronized over the air to give roughly 1 microsecond alignment of time across all the devices. With this kind of alignment, you can do real-time control. So here it's turned off the synchronization, and you can see it just doesn't do quite as well. So this kind of synchronization across the network is key to many characteristics that are going to be required for industrial IoT automation. But having timing in this level changes the game. Okay. So another example is once you have this kind of alignment, you can do what we call multipoint. So essentially, it's a multiple antenna system now. All the transmission points are synchronized, and so you can get multiple antennas serving devices at the same time. And the point of this is, of course, reliability. So if you have a blockage or something like that the other links will maintain the reliability of the link, and this is how you're able to achieve real-time control. Now, of course, it would be even better if you could predict this kind of blockage and then adapt accordingly. But that, of course, requires positioning. So this is from the latest Mobile World Congress. So we've done experiments with positioning using wireless networks in the industrial setting. And so one of the surprising results was that even in a highly dispersive environment, a highly multipath environment, it turns out that with machine learning, essentially taking into account the multipath nature of the environment, you can actually do much better positioning than we could do before with more traditional methods, such as time difference of arrival. Okay. So all these elements now will eventually have to be brought together into a single system. And so this is kind of the framework we have in mind for these private networks. So in the beginning, you have a digital twin built with various kinds of sensors. That forms the foundation. On top of that, you have all the applications that you might want to run in the environment. There's sensing, RF sensing like I just showed you, but might be other forms of sensing like cameras. All of that information is made available so that you can do configuration of real-time control. And that and the real-time controller would then adapt to the needs of the applications, like I showed you earlier, synchronize things that need to be synchronized, provide redundancy where it's needed, sacrifice capacity for reliability when it's needed. And all of that would be managed by an orchestrator piece of software that sits on top and understands all of the trade-offs, all the resources, and the applications, and knows how to configure to get the best performance and to meet the requirements. And I think from our perspective, this kind of forms a nice template for what we think the wide area network of 6G might look like. So, yeah, so we see this transition from 5G to 6G. Is probably the best way, at least that I can understand it, is that the private network I just showed you becomes the wide area network. And it's a big challenge, and hopefully we'll be able to do that in the next few years. Okay, thank you.
Thank you very much for this Very interesting and quite detailed explanation of how this is going to work. No questions? We have time for one. Please.
Can you hear me all right over there? Great presentation.
Microphone.
Okay, sorry.
Does that work? That's great.
Yes.
Mike Short from the UK. Great presentation. Clearly the importance of positioning and timing changes, but you didn't really refer much to coverage and satellites and the competence that Qualcomm have in that area. Could you relate satellites to any coverage requirements? Could you also relate the importance of position and timing the way you see it moving forward?
I mean, two satellites, position and satellites?
I would start with satellites and then cover positioning evolution.
Okay. Okay. So yeah, Qualcomm has an interest in satellites, and we've worked with OneWeb quite a bit directly, and we're interested in making sure that providing satellite links on the handsets is one of the things that's happening now. So it's quite different from these areas, and I think it's an important aspect of the system. I think that I don't see a very big connection between positioning and at least fine positioning, of course, in satellites. I think for satellites, of course, you have to worry about things like interference and spectrum, and there are all kinds of regulatory issues. In that sense, positioning is important because you need to make sure that you're managing interference and it's a geographic phenomena. But positioning in like using RF sensing to do positioning for the industrial setting, that's a different game. Like the scale of accuracy we're talking about is very, very different. Right? So I think on the satellite question, I think maybe I'm not the right person to ask. I'm not really an expert on what Qualcomm is doing in the satellite space. I know it's important, and we are looking at non-terrestrial networks as part of 5G, but I really don't have a whole lot more I can tell you about it.
Thank you very much.
Okay.
Thank you. Thank you for the question. So now we are moving from the technologies and research opportunities towards with Professor Fredrik Tufvesson from Lund University. Please, the floor is yours.
Thanks. So I'm very happy to be here, and now I think we have already got quite a good introduction to where we are going and why we need 6G, and what is really pushing us to a 6G. And as you know, you have heard that, okay, the AR/VR pushing for lower latencies and also higher requirements. We have the digital twins. Not to forget also the other aspect of it. It's not just about getting more and more and more. It's also about getting less. How can we serve those energy neutral devices and actually also have a sustainable 6G? But let's go into the technology. And as you know, I mean, the demand for data is growing and growing. And I mean, we cannot change physics. There are a number of tricks we can use in order to increase the capacity. We can densify the infrastructure, increase the number of base stations access points. We can move to higher frequency bands, not because we want, but because we have the bandwidth available there. So in case we need the higher bandwidth, then we can go up to the high frequency bands. And then we can use the more and more cooperative antenna elements, massive MIMO. And for 6G, I mean, as I said, we cannot change physics, but we can use those tricks even once more. So we densify the infrastructure even more. We go to even higher frequency bands. We go to more and more cooperative antenna elements, and now we also distributed them in the environment. With the distributed antennas, we can actually select the ones that are currently effective, and then we can focus the signals to where we have the users. And in the same way as we do with massive MIMO, besides creating clouds of signals, we can also create clouds of non-signals where we don't want interference. So we can actually both control where we have the strong signals, and we can control the interference in this way, if we have control of the channel between all the users and all the antennas. A little bit from a technology perspective, where we are up in this corner with massive MIMO, then with some new flavors, extreme MIMO, we have ultra massive MIMO and holographic MIMO. a little bit different flavors, more antennas, either you put them denser. To be honest, I don't think there is so much that you can gain about that with that, but rather increasing the aperture, more antennas, that will actually increase the capacity. Then we can go to the right, staying in the mid-band at the lower frequencies, but we distribute the antennas. Then we go to this distributed MIMO, large intelligent surface, cell-free massive MIMO concepts that you maybe have heard of already. Going up to in frequency, then we have the millimeter wave, and then we have the sub-terahertz. And I would say that the millimeter wave, and especially sub-terahertz, it's really where we have extreme high requirements of data rates, because there it is tricky to get coverage. The coverage we have to create with the lower frequencies. We cannot create good cellular systems only relying on sub-terahertz. It won't work. And what's also, as we have heard, we have the joint communication and sensing. And here I would also like to stress a little bit that I think when we are talking about sensing, let's build a communication infrastructure that is very good, and then we reuse that for sensing. I don't think we should have a separate sensing infrastructure and separate communication infrastructure, and I don't think we should take away some of the good properties that we have learned when it comes to communication just to get a little bit better sensing. It's better that we learn how to do effective sensing with the nice signals and that we have available. So, going up in the top left corner here, massive MIMO. One thing that I think has not been stressed or not been looked so much at is what we actually get with the massive MIMO. When we coherently combine the many signals that we have there, we get both this array gain, that we get a stronger signal, and with this is an example with 128 antennas at the base station, and we gain 20 dBs, 100 times or so, just by coherently combining the signals. But what we also get, if you compare the yellow one, where we have signals combined, and the bottom one, you see those signal variations. They are gone, and that is what's called the channel hardening effect. And you can see that we get this both in time and in frequency. So this, what I learned when I took my first wireless class 30 years ago, Rayleigh fading is gone. Maybe we can rethink how we actually transmit and how we code the messages in the network if we get rid of these fading problems that we are used to. This is an example from a quite extreme factory environment, a lot of metallic objects, and if you look carefully, you see the base station there. This is a co-located one, and this is the ugly distributed one. I'm sorry for the ugly antenna design there, but this is just our first trial. What happens actually when we distribute the antennas? And can we create reliable ultra-low latency communication? Also, here, if we go behind those machines, where I think it's one of the most tricky spots in such an environment to create reliable communication. So we went there, and then we scanned, and we took 1 million samples or so, and then we looked at how does the samples look like when we combine the 128 antennas or 100 antennas together. And this is, we go behind this machine there at the time after a few seconds, and then basically the variations are gone. And here we are scanning and scanning and scanning, and we cannot find a single spot where we don't have a good signal. And with just a few dBs of fading margin, we have a well-working system without any retransmissions. You have the co-located system on top, you have the distributed one. The distributed one there, you have some antennas not being so effective because they are not aiming towards the user that we have in the co-located case. On the other hand, what we get with the distributed one is also that we have a little bit more of protection against the large-scale fading, because the signal is coming from all different directions there, and we also can get some protection against shadowing. If we look at the statistics, here you see what's happening with 1 antenna, 2 antennas, 4 antennas, up to 100 antennas, and you see we have an enormous diversity. And with just 4 dBs or so, we have overcome all the fading problems there, and there are no outages left. So that is basically where we are today. And if we now take this one step further, then we reach this distributed MIMO, large intelligent surface, radio waves. There we have the robust and scalable applications with real-time dependable on efficient usage of the energy and the bandwidth. Because here we can really use the antennas that are more effective, so we don't need to use the ones where we have somewhat higher path loss. We can always find some antennas that are really effective. Let's take a theoretical example. So this is from our reindeer project. So what you see here is that we take this radio stripe concept that Ericsson has been working with, and we apply it to one strip along one wall, along 4 walls, and then we have 4 stripes, 4 stripes along the walls there. And then we can see what is the transmit energy needed in all of those cases. And just compare with a single co-located base station in the middle of the room that we have here, and with the distributed antennas there. There is an enormous potential of how much we can decrease the transmit energy with this technology. Then, of course, the question is, does it work in reality? How does it look like in reality? And to investigate that, we made an investigation. So we created a virtual large array with 15,000 patch antenna elements along 2 walls, and then we had the users distributed there in the middle. And with this, if we look at just how does the received energy look like? So for one user, the one we have over here, then you can see that you have strong signals at the walls closest to you, as expected. And for another user, here are the strong antennas here. So for different users, we can actually activate different antenna elements, and then we let the group of active antenna elements move with the user. And we cannot only just move the transmission and reception like this, we can also move the compute resources when the users are moving, so that we actually let the applications somewhat follow the users. Looking at another aspect, so if we now try to use this infrastructure, and then we focus the energy towards the users, and we take the 16 users, we line them up along the wall. And this is how when we aim for one user, for example, this user over here, how it spreads to all the other users, with either if we have one wall active, if we have 2 walls active, and with different orientations of those 16 users. And you can see that we can actually create a cloud of energy that is very narrow. It's about 10 centimeters or so, which means that we actually can feed those energy-neutral IoT devices also at the distance. And we can do that without violating or to create too high electrical fields around the antennas, because the signals, they add up where we have the users. So there is actually quite some potential when we have this distributed architecture. Going further, if we now have this and then we let the user move, and then we see how does the signals actually look like, what are the signal strengths? And we pick then 12 antennas in this infrastructure here. And then you can see here, as expected, when we move, the signal varies quite a lot. But if the top red curve there, that is what we get when we combine all the signals coherently. And you can see that we have a very nice, stable signal, always good. And this is just with the 12 antennas, and you can imagine if we then have 100 or 200. Next thing, sensing port. What we have here is also a distributed bistatic or multistatic radar system. So if we let all the antennas listen to each other, so when we transmit with antenna 1, if all the other antennas listen to what it receives, then you have one radar system. And then you do the same thing when antenna number 2 transmits, you listen with all the others, then you have another radar system. And you can see here that when we now let the device-free person, walk in this environment, and then you can see the signal variations there, and it would be quite straightforward actually to pinpoint where this user is located just by looking at the multipath and how it varies over time. We can do it with parametric methods, or we can do it with machine learning, as previously pointed out. So a little bit where we are heading, it's maybe a device like this, not so much more complicated. see if I can open it. Not super fancy. So 16 and 10 elements. We have them in the room here. Maybe 10 of them. They communicate between each other. They synchronize, of course, in time and frequency, because they have to jointly send the signals so that they coherently combine where we have all the users. They could do the sensing, and when we are moving, we activate different of those antenna units to actually follow the users. And in that box, we also have the compute and storage resources so that we actually can do this edge processing and that we can do the AI-enabled things already from start. So we have the communication capabilities, we have the positioning capabilities, and then we also can do the power transfer there to the energy-neutral devices. Maybe something like this, and maybe we can use technology that we already know how to do. Maybe we can use cell phone technology in those devices, and maybe we are at power levels of a watt or something like that, so that we are actually not increasing the overall network power consumption. Well, this is of course not the only way. Other things going around. One interesting thing that actually took place also 10 years ago was investigations. What happens if we go down in frequency, or if we stay at, say, 6 to 15 gigahertz? And there were a lot of investigations, and especially comparison between 30 gigahertz and 15 gigahertz. But then all turned out that it was really hard to get access to those frequencies. Maybe we'll see what happens in World Radio Conference this year and in 4 years, whether it's possible to get access to some of those frequencies at a worldwide basis. Interesting thing, I think, is that, I mean, here you can see how much we lose when going around the corner there, around 28 gigahertz. If we now do a measurement or simulation at 15 gigahertz instead, then you can see that there is actually quite a big difference in the 15 gigahertz behavior and in the 30 gigahertz behavior. And in this 6 to 15 gigahertz range, we are actually somewhere in the middle to what we are used from the ordinary cellular systems and the millimeter wave systems. And we can actually, I think, create quite good coverage at this band between 6 and 15 gigahertz. Finally, going up a little bit in frequency to the sub-terahertz region. This is based on measurement at USC by Abbas et al. And this is just an example of an impulse response. And for those of you not being able to look at impulse responses, what you see here is the line of sight and the different multipath components that we have there for between a transmitter and receiver at the distance of up to 100 meters. And you can see there is a big line of sight component, the early one, but there is also a lot of other components. And depending on which antenna we have, if we have an omnidirectional antenna, the blue one, or the red one, which is beamformed, then we see different things in the channel there. And if we don't have the blue one, we have to look for where do we have the good channels. And once this channel is blocked due to one reason or the other, we have to look for other channels so that we can maintain the communication. This was in line of sight. Going to non-line of sight, we can see that still it's possible. We do have similar behavior there. There is a huge difference in between the blue omnidirectional and the red directional channel that we have there. And we can live on those reflections, and even smaller reflectors, they play a role there, but they come and go, and we have the shattering issues there. So if we look at the received power levels that we have in such a network, so this is at different distances from a couple of meters to 100 meters. And the green one is the theoretical line of sight case. The blue one is the fitted curve there, and then we have the red one, that is the directional channels where we have beamforming antennas. The blue ones are the omnidirectional one. What's interesting is you can hardly see the difference between the received power levels that you have at 10 meters and 100 meters in some cases because of this shadowing. So I would say that at 100 meters, yes, it can work, but most often it will not work reliably. in order to get reliable communication, maybe we have to go down to the 10, 20 meter case. There, I think we can get reliable communication in extreme cases where we really need the data rates. Otherwise, to get the coverage, I think we have to stay at the lower frequencies. Well, to sum up, I think, as always, it's a trade-off between spectral efficiency, cost, and not to forget energy efficiency. We need to get the total power consumption down. And massive MIMO, I think, is really an enabler for the ultra-reliable low-latency cases, and especially if we then distribute the antennas, because then we get the protection also against the shadow fading. Sub-terahertz, going up to the high millimeter wave bands, yes, it is possible. You can get communication there, but to have reliable communication there, you have to limit the distances quite a lot. Indoor line of sight, for sure, can work if you have the requirement for the high data rates. And finally, I think also I should highlight that this sensing that we can do when we distribute the antennas, then we have a very nice multi-static radar system, and we can do pretty nice positioning and sensing in that network. Well, with that, I would like to say thanks.
Thank you very much, Fredrik. Time for one question or two, if you have. If there are no questions, then we will... Yes, there's a question, please.
Thanks for the nice talk, Fredrik. You didn't touch so much on smart surfaces and how they could complement and perhaps change the channel, or what do you think about the potential for smart surfaces?
If we take the intelligent reflected surfaces, then I would say, I mean, there is a lot of talk about them in academia. In my opinion, technically, yes, we can implement them, but I'm not sure we have a business case, because you have to compete with the smart repeater, and both of them need power. They can not be passive, because they need a lot of power, and you have the channel estimation problem there, especially with the large intelligence reflective surface. So I would say, in my opinion, I think that the smart repeater will win, and I think also that maybe the channel is not sparse and spatial enough for the reflective surfaces to really be effective. So I wouldn't bet my money on them, but I know there is a lot of interest in academia for the races.
Thank you very much.
Thanks.
Very interesting discussion about future prospects of the technology and the development research. We are here, we have organized this symposium between our academies for the reason that we would find opportunities for collaboration. And so the next session, or the next part of this session, is a discussion about, a panel discussion about potential areas of collaboration and opportunities for those between US and Swedish innovation systems. And so it's my pleasure to invite our next guest to moderate this panel, Professor Dr. Murat Torlak from NSF, please. The floor is yours. Thank you.
Thank you. Audio check. I guess you guys hear me, since I don't hear any complaints. Murat Torlak from NSF. I'm a program director on a temporary basis at NSF. My regular life, I'm a professor of electrical engineering at the University of Texas at Dallas. When I heard the earlier talk, it was music to my ears. You know, I was very happy to hear some of the newer developments on wireless communications. But today, I'm here to moderate this interesting area of discussion, to discover some of the potential areas of collaboration between US and Swedish innovation, the systems. In U.S., National Science Foundation funds basic research, including wireless communications. And in the panel, we have participants both from Sweden and U.S. Annie Lidgard, we just met via email, so if I cannot recognize the person, I apologize. And Christan, Hedelin, hello. Luis DaSilva, and Dimitri Perolis. All right, thank you. So thanks for all that introduction. I guess we'll take turns, and I'm just gonna go over a few slides. Perhaps then you guys can step in and talk about your experiences, your point of view, and somebody will try to moderate the time, I suppose. So let me get started. First, I like to spend a little bit of time on what NSF does, some of the one collaboration example between Sweden and NSF. U.S. National Science Foundation is an organization, is a federal agency, the funding agency, that promotes progress of science by investing in research to expand knowledge in science, engineering, and education. And its budget typically increases. You see a dip in FY21, but its budget, it's somewhat steady, but it increases depending on how the Congress sees the importance of making investment in certain areas of science and engineering. As a primary funding agency of basic science and research, many US-based researchers, scholars, postdoctoral researchers, graduate students, undergraduate students, trainees, teachers are funded by the work that is supported by NSF. While most of the research goes to academia, universities, NSF does provide funding for small businesses and startups to mostly translate the research being discovered in universities or nonprofit organizations. NSF consists of 7 science and engineering directorates and 3 interdisciplinary offices. As you see from information technologies, including science and engineering, to like core, pure engineering, mathematical and physical sciences, biological sciences, geosciences, including polar programs, social and economic sciences, up to our very brand new directorate, Technology, Innovation, and Partnership. I'll spend a little bit more time on that new directorate because it's relevant to our current discussion. Through these directorates, we fund research. Each of the directorate is further divided into divisions, and each division has multiple programs depend on the scope of each division and the supports. So here, I am giving an example of one of those divisions, computer and networking system divisions that I'm part of. The CNS division is part of that, one of those directors, 7 directors that I showed you earlier on the slide. You see a lot of acronyms, obviously. We are not really creative. We cannot come up with names like reindeer or something else. But this collaboration perhaps can achieve that, can fill that gap. What you see in the block on the left, you see CSR and NETS. I am part of the NETS program that mostly oversees research on wireless communication, but more networking focus. Because if you want to get a research support on circuits, for instance, you want to design the next generation of terahertz receiver that mentioned earlier, you have to go to a different directorate which funds engineering research projects. But within each division, there are different programs that would focus on, for instance, creating an infrastructure and wireless, infrastructure on conducting research on wireless communication, next-G wireless communication. Or if you want to include undergraduate students in your research, you go to a separate program, get funding to involve those students. The reason that I'm mentioning, giving this an example is that if you want to collaborate, we have to find an existing mechanism within NSF not to duplicate what we are doing. So if you want to, do workforce development, for instance, then you may have to go through our research experience for undergraduate, program. As I said, we also fund centers like large-size centers such as AI, Artificial Intelligence Institutes. They are about $20–25 million investments over 4 or 5 years. We also fund infrastructure projects such as POWER program. You'll probably hear about POWER later during the conference, which is a platform for advanced wireless research. Although I said we are not very good at acronyms, time to time we can come up with a really nice acronym that sounds really, really good. POWER is one of them. So the program that I'm part of, the NETS program, this is the program that funds network-specific research. Again, tries to tries to scope the project that funds, because we cannot just fund every type of wireless proposal that comes our way. We want to fund projects not only in wireless but also wired, right? Because everything goes together. Starting from IoT, terahertz networking that you have heard just recently in the previous talk. But you have to have that networking element flavor if you want to qualify for my program. I mean, if you want to get funding from my program. So you have to have that addition. What's the benefit of doing that additional shadowing work, for instance, within the networking perspective? But on the other hand, we do realize that investments in doing a successful research in next generation networking has to cover multiple dimensions. Nowadays, right, we have to fund some work in AI, ML. Computing has to be there. Without compute resources, how are you going to run your Open RAN? Basic, more fundamental communication theory, right? That theoretical understanding has to be there. And more we are seeing the importance of data sets, creating data sets to enable verification of some of the algorithms, AL, ML algorithms, with some data sets that have been created by the community. But we have to create them. We have to keep them under accessible. So we have to make sure they're accessible to all the researchers. And the hardware, software have to be there. Again, how do you verify the algorithms or ideas that you come up with? We need a shared test beds. And then you have to be able to access the spectrum to try them out, right? You cannot just keep doing things in the lab. So what we try to do is, at NSF, try to cover all of these different aspects. And a partner and collaborator partner can come in and form a partnership, either one or multiple of these dimensions, to expand the knowledge space for both sides. As we are advancing the next generation research, as I mentioned earlier, we are fund research at different scales, not just by ourselves, but via forming domestic or international partnerships. One way that we started doing more partnerships is the domestic partnerships, either doing one-to-one partnership. One of the programs that we created, it's about to end, is ML WINS program, Machine Learning for Wireless Networking Systems. We co-funded multiple projects with Intel, and to investigate the potential of machine learning, AI for improving wireless communications. And last year, we made the first awards on the RINGS program, which is a partnership between multiple companies as well as few U.S. federal agencies. We also fund research infrastructure. so that our researchers can test and verify some of the algorithms. For instance, the power platforms, testbeds, they are city scale, and they're open to actually every researcher. You don't need a MOU, between memorandum of understanding between Sweden or US or NSF for your Swedish researchers come and use any of the power platforms. They are open to any academics in the world. So some of our infrastructure facilities are actually open to every researcher. So those opportunities, collaboration opportunities are already there. We also do center scale activities, and as academics, you should be able to collaborate with any of the centers as well. More importantly, perhaps the international partnerships. We do have partnership agreements with several countries, and we are, although my program does not have a specific agreement with any Swedish organization, but we are working towards that. But my sister directorate, I'm probably going to skip this slide in the interest of time. The NIV directorate, which is a directorate of technology, innovation, and partnerships, is newly founded about a year ago and headed by Dr. Gyan Chandani, and they have only one division for now, but they are looking into expanding it. In fact, their plan is to include more division, more pathways for technology translation, and also increasing the number of innovation and technology ecosystem through new investments. And they did take over some of our existing investments, and they realigned them with the new directorate. One of them is Convergence Accelerator, which is the program that actually includes a partner from two partners from Sweden. And through that, here I'm listing what it involves. It's a rather new announcement. It just came out last month that NSF will collaborate with two Swedish government agencies. One is Swedish Research Council, other one Vinnova, on the topic of real-world chemical sensing applications through our Convergence Accelerator program. This is a program that tries to facilitate that the ideas developed in the lab and accelerate their development into more product, more marketplace. And in fact, our director, NSF director, Dr. Panchanathan, did say that he's very happy, and NSF, and he is delighted that NSF is partnering with Sweden. Together, we will synergize our research and innovation communities to strengthen interplay between our countries and to enhance the full cycle of discovery and innovation. And I'm thinking, why not expand on this and think about, what can we add to this existing the partnership on chemical sensing. So today, in fact, this morning, I was in discussion with my colleague, Marco, from Vinnova, to continue on the discussions, on the technical discussions on wireless communications and what we can do, and try to sort of develop the parameters of the collaboration. And if we can agree on those parameters, perhaps then work on implementation plan to outline the specifics of the collaboration and then associated the mechanics. With this, I'd like to end my the presentation. If you like, I can perhaps take the questions later after other presentations so that we have more interactive, I guess, discussion. So with that, I'd like to invite my next speaker. Oh, all of us here? Okay.
Looks like we're not going to have slides.
So move maybe the table a little bit this way to create space.
Sure.
Sorry.
Sure.
Go ahead.
Thank you.
Join you.
Yes. All right. So I guess I'm going to let each speaker to introduce themselves. At least the audience get to know who you are.
Yeah.
Let's get started.
Okay, so Christan Hedelin, Head of Strategy and Technology at Saab Group.
Hello, I'm Dimitri Perolis. I'm incoming Senior Vice President for Purdue University Online.
And hello, everyone. My name is Ann Lidgard. I'm the Director of International Collaboration at Vinnova, and I'm also a fellow here at IVA of the Division for Basic and Interdisciplinary Sciences.
Hello, I'm Luis DaSilva. I'm the Bradley Professor of Cybersecurity at Virginia Tech, and I also have a role as the Executive Director of the Commonwealth Cyber Initiative in Virginia.
All right, thank you. So I guess we wanted to start with either your personal experiences, of the similar collaborations or partnerships between U.S., Sweden, and how can we expand on those experiences to maybe start a new collaboration.
Yes. So I'm happy to do that. Being mindful of time, I will be fairly brief, I think. But Saab, working a lot within the defense and security industry, of course, we are very proud to be partner of the T-7 fighter trainer program that we do together with Boeing in US, and we're building that in West Lafayette, and then have a very good collaboration, research collaboration with Purdue as well. So I skip all the things we do. What I think we should do is to look on how 5G and 6G technologies can enhance the business that I try to support our customers, and that's the future battle space. And I think we need to, in future, merge the different physical domains with space as well as a cyber domain, and for that we need significantly better connectivity. And here we're talking about going from kilobits per second to gigabits per second. So it's like 6 orders of magnitude. And I think we can do a lot there because we have the best compute cloud industries in US, and we have the best connectivity industry in Sweden and perhaps the Nordics then. And I think that I see a couple of very interesting areas. One is, of course, to look what can we do when it comes to joint all-domain operations, and what role can 5G and 6G play in that type of future battle space solution dimension. I think that is one very important area. Another area which I'm very excited about is the range finding and sensing that would be possible if you adopt the waveforms and adopt the receiver chain a bit on 6G. We have a strategic partnership on research with Ericsson, and we're looking on how we can turn 5G apertures into radar and sensing apertures. We realize that we need to do a bit of work on the receiver chain, but I think if we start early, jointly, we can do a lot to create actually a radar and sensing mode in the 6G networks. And if we manage to do that, we will have a range finding and sensing network with tens of thousands of apertures spread around the terrain. And I think that turns to the last suggested area of collaboration, which is actually advanced air mobility. And we are doing a lot of work, financed and sponsored partly by Vinnova. Here I see Darja here. And we're doing that together with Ericsson, Luftfartsverket, and a couple of research institutes in Sweden. But here I think we can do that together with US academia and industry. And what that allows and what that vision entails is actually that we can create the coverage above rooftop to, let's say, 3,000 feet or 10,000 feet in order to allow autonomous platforms to work in a mixed air domain, both civil platforms as well as military. And that will be a real milestone. And I think one realization I do is that you really need to have a network connectivity that is mission critical in order to make such a system work. So range finding and sensing, advanced air mobility, and then of course connectivity, mission critical connectivity, those 3 areas. Thanks.
Okay, thank you. Dimitri?
Yeah, thank you. So I guess from a university perspective, I wanted to give you a couple of examples that we are seeing, I think, big success at Purdue of bringing industry in the university environment and also launching startup companies from there. So the first one is called Discovery Park. So Discovery Park is a massive 400-acre area on the Purdue campus that actually works more or less as a live, work, and play environment. You can actually access all kinds of technologies that are happening at Purdue. You can bring your own technologies. You can actually live there. There are actually hundreds of houses right now, and I'm not a real estate agent, but if you really want to move to West Lafayette, this is the hottest spot right now to actually come. It's an area where you can actually get space. The companies can work with university researchers hand to hand. And this is an area that actually sees a lot of growth, a lot of opportunity, but a lot of real-world success as well. And that actually brings me to the second example I want to give you, and this is what we call the lab-to-life concept. So for those of you who may not have had the pleasure of visiting us yet, you may not know that Purdue is actually operating its own airport. There are actually about a handful of airports right now in the United States operated by universities. Purdue actually had the very first airport in the United States about that. In fact, Amelia Earhart was an instructor at Purdue. She was actually there as well. That airport is actually the second busiest airport in Indiana right now, with more than 125,000 operations per year. So we actually partnered with Saab and Ericsson to create the first, what we like to call, lab-to-life concept. The whole idea there is to introduce a private 5G network in the airport and essentially prove all the research that we are doing in a real-life scenario. Prove all the technologies that companies are building in a real-life scenario, and then scale it, having the confidence that it actually works to a much larger project. So Ericsson, for example, is helping with creating the 5G network. Saab is helping in launching platforms for the efficient operation of the airport, security operations, and of course Purdue is bringing the researchers, but also the running of the airport as well. So this project was actually announced March of this year, March of 2023. It's a super exciting, I think, example of how we can take universities and make them partner with industry together to create what I like to call the 1 + 1 = 3 partnership. So I could bring more examples in the Q&A, but just wanted to start with those two.
Mm-hmm. Thank you. Great, thank you. I thought I might start for the benefit of our foreign guests joining us through stream, just to say a few words about Vinnova, because you may not be as familiar with us as the rest of the audience here. So Vinnova is the Swedish innovation agency. We are a governmental innovation agency, and we report to the Ministry of Climate, Energy and Enterprise. So our mission is really to increase Sweden's innovation capacity for sustainable growth and for the benefit of society. And we do this in several different ways. We identify areas and challenges that need to be addressed. We mobilize the stakeholders that have agency and also have the motivation to actually make change and drive the change towards a more sustainable future. And then we also have our grants. We have a grants budget of roughly $350 million that we can provide through calls. And the type of projects that we finance can be anything from 10-year commitments for pre-commercial industry, academia collaborations, like competence centers, going all the way to the very short-term proof of concept type projects that we offer to startups to get innovation going and to get the commercialization out of the universities. So that's just a little bit about Vinnova. We're extremely committed to the green and to the digital transformation. And we have some major programs now starting in advanced digitalization that I think can be really interesting for this topic as well. Over the years, this is going to be a multi billion crown type of program, so quite extensive, together with industry players like Ericsson, ABB, Saab, so that we're very happy about that. So Vinnova and our predecessors, we've played important roles throughout the evolution of wireless, ever since the creation of the Nordic mobile telephony system back in 1981. So we have quite a tradition of actually...
You are generation zero.
We are generation zero. So we've been, a sponsor and a support for this type of, creating the ecosystem, I would say, in Sweden, which is really, really strong and which really can, I think, pave the way for a very fruitful collaboration. Both the industries that we have, and you've heard some examples today, but also the universities, some of which were on that the PowerPoint earlier. And I think, so I mean, personally, I've lived over 15 years altogether in the US, and I think we all recognize also that the cultural barriers to working together between Sweden and the US are actually quite low. So it's a low threshold, and I see you nodding here, and there are many, many examples already of very fruitful collaborations, of which we've heard some here. So 6G, I mean, it's extremely fascinating. I mean, it brings wireless to a whole new level and dimension, and of course it's going to transpire throughout our whole society. And I'm not going to discuss the technology, but rather, I mean, I think what's really amazing with moving to 6G is how it really opens up the whole area of innovation in many, many areas. Because if we don't really look at the applications that, we've seen examples that are quite mind-boggling here, that's going to drive the demand, right? That's going to drive the need for the networks and the technology and all that. So this is, I think, also an area where we can maybe provide exchanges also in the applications area moving forwards. And this is where test beds, of course, are extremely important. We have some in Sweden also for autonomous air flight, which is going to require a lot of these technologies, right? Many other test beds that we are willing to enable to. And you mentioned, of course, the MOU that we have with NSF. I think that's an amazing step forward. And now that we're discussing also expanding, I think that's going to be really good. So maybe I'll just stop here for now and let you take the word.
Okay, thank you. So when I was thinking about the panel, I remember that my second PhD student actually finished up at Virginia Tech and moved to Luleå to be an assistant professor at Luleå Institute of Technology. So that was around 2004. So I guess my collaboration in Sweden dates back about 20 years. But more recently, Virginia Tech joined as a US affiliate member a program called SIREUS. It's spelled SIREUS, which is led by a gentleman called Christan Bergman. He's based at the House of Sweden in DC. And it's a program of the Swedish American Chamber of Commerce to increase collaboration between Swedish institutions and US institutions. So there are 13 Swedish universities. I promised Christan that I would do a little bit of an ad since he's not here today. But there are 13 Swedish universities that are part of SIREUS. And at the moment, there are 9 US affiliated members as well. And the idea is to stimulate movement, mobility between the US and Sweden, of students, of researchers, joint research, and so on. It's a framework, so on top of that, there has to be some mechanism for funding so that this really grows and happens at scale in terms of research collaboration. So before going back to Virginia Tech, I was based in Ireland for 11 years, and I was always a little disappointed that the Commission didn't have a more robust way to fund research across Europe and the US. There are some mechanisms, but they're not really at large scale. But NSF has a lot of successful, I think, one-on-one relationships with Finland and Ireland, Northern Ireland, etc., that Murat mentioned. I benefited from some of those programs, was funded under some of them, and it's really great to hear that there are these discussions with Vinnova and the Swedish Research Council. I think that's what really is required to underpin this more lasting collaboration. And then since we were asked about potential areas of collaboration, I wanted to make a quick pitch for two. So one is, of course, 6G. We're going to hear a lot about different technical challenges and research areas, and they all would make fantastic collaboration projects. But I also think that we should think more broadly, since the timing is right for the visioning of 6G, about how 6G will actually reflect the values of our societies. So how do decisions about everything from spectrum to density of deployment and so on, how do they affect things like sustainability, the things that we claim to care about? How do we navigate this trade-off between security and privacy? In terms of innovation, whether open interfaces and disaggregation more in general, will that really lower the barriers to entry for deep tech in 6G? So I think the time is right to think really broadly about what the architecture of 6G and the underpinning technologies will look like, and I think that would make for a really good topic of collaboration between the two countries. And the second area, since in the US I lead this group called the Commonwealth Cyber Initiative, and we focus on cybersecurity, so I need to make a pitch for cybersecurity. And of course, again, there are lots of technical questions that make for very meaty research topics. But some of the really interesting questions, I think, happen at the edge between the computer science and computer engineering part of cybersecurity and the other disciplines. And we were at KTH earlier hearing about digital futures, and some of the examples that I really thought were interesting were where researchers were put together across disciplines to solve some problem. And we've seen the same in my organization. So we have a program that matches artists or researchers in the arts and design with researchers in cybersecurity. And it ends up resulting in very unexpected types of innovation. We're seeing similar things in AI, of course, being a huge question at the moment. So trustworthy AI, AI in democracy, AI in the spread of information, AI in general, and how it changes society, what kinds of regulation might be in order for that, and so on. And I think that's another really big topic where some of these common areas of culture between the two countries could be explored to build a collaboration. So I'll stop here.
I completely agree with you. I mean, these softer issues also that are related to 6G are, of course, incredibly important. And I mean, now we're not talking about transformative AI, right, that actually transforms our societies and maybe the way we relate to one another. And I think for 6G to really be deployed the way we envision, we have to have some guardrails or some solutions, or at least have had taken into account some of these issues as well. Like we're talking about the cyber-physical continuum. Questions like, how do we know who is a deep fake? How do we know who is a real person, who is an avatar? I mean, to really just make sure that these things become transparent and straightforward, I think is going to be incredibly important if we really want to see this broad deployment the way we envision. So taking also those questions into account, that would be a really...
In your example about the deep fake, I was reading about some research about how to identify that the video is not a real person, and they were using the physiology of the body and the fact that, as blood circulates, this changes and some of the tone of our skin color, and you can detect when the video was manipulated, and not a real video. And so all of these will really require that we work closely with, in this case, health professionals, but it could be psychologists, sociologists. Ethicists everywhere.
Philosophers.
Well, thank you all. I guess we can open the floor for questions. I have few questions, but some of those questions I thought they were already answered because I was going to ask, for instance, who are the other key stakeholders besides government agencies? You did mention that interesting project at Purdue between Ericsson and Saab, and additional, perhaps mutually beneficial other exchange opportunities. You did mention that program series, program that has 13 Swedish universities and 9 US universities. So it looks like most of my questions were answered in the introduction, but so I'm going to open the floor for questions. Yes.
My name is Mohammed.
There's a microphone next to the seat.
Hello, my name is Mohammed Imran. I'm from University of Glasgow in UK. So just wanted to ask that we are talking about mobile systems, and mobile systems require some collaboration in terms of having common regulation as well as common standards. So any transnational collaboration in this area is really, really important. And we are talking about at the moment just collaboration between USA and Sweden specifically. So is there a scope of widening this collaboration between Europe and USA, including UK as well? And what will be the right way of doing that?
I can start, even if I'm not an expert in regulation. But I would say that I think the important thing to find new groundbreaking innovation is about having different application experts, domain experts, meeting together with technology experts and regulators. Like if you look at advanced air mobility, for instance, you find things that you didn't believe was a problem when you have the different stakeholders looking at the technology. So one example that I find is very interesting, and I know some of the audience here have heard me talk about this before, but when we worked with this advanced air mobility, the Vinnova project with Ericsson, ourselves, Saab, then, and Linköping University, and Luftfartsverket, the Aviation Authority of Sweden, they said that in order for you to run an unmanned flight beyond line of sight, you need to be able to comply to that if it falls down, not if, but when it falls down, it doesn't hurt anything on the ground. Then in that meeting, we had experts from Ericsson and on 5G say, we know how the ground situation looks like through the 5G network. And that is how I think we can move regulations and standardization forward by having those diverse teams looking at a potential solution to a problem and then verify that through other lenses where there are regulators or other technology companies that has a solution or a problem that can be solved. So I think in my view, the success of GSM 2G was that we all had a wish to have efficient, cost-efficient, and attractive mobile phones, but we couldn't build a system in every nation across Europe. Then we need to settle down in Sofia Antipolis and sit down with a list of requirements from all the different nations and operators together with the companies, and then we found a standard that actually worked. And then we could compete building systems on that standard. I think that modus operandi, I would like to do more. And I think in 6G, it's important that we have those different domain perspectives looking at the different applications areas or potential customer problem and market opportunities early. Because if we do it early, it's possible to do things. And that is why I'm so excited about being early.
Yeah, and perhaps I could add just a couple of thoughts, and I completely agree. Just wanted to mention that the universities, I think, have a critical role to play there. I can bring as an example the NextG Center at Purdue that is focusing on 6G right now, led by Professor David Love. One of the things they actually plan to do next month, in July of this year, is actually issue the first non-partisan report about the 6G, right? And this is done in collaboration with many companies, including actually Ericsson and Nokia and Intel and several others. But I think this idea of bringing people together under umbrellas of that nature can help a lot towards that area.
I also want to mention that there was earlier mentioned that cultural differences or some differences, either politically or the way that things are done in both countries, and standards are actually one of them. If you, in my talk, if you saw, I didn't mention 6G at all. I didn't mention any when we're funding research. Our researchers can, come and propose some research that they can claim that they might, that particular research may go into this and that standard. But NSF role and mission is not to promote certain standard or certain technology. So our role is just to fund the basic research and let the marketplace and the rest of the government to get that research and try to use it in the best way possible for the nation and for the societal good. So that's why we sort of try to stay clear of all those standardization discussions and any other relevant policy or regulation issues. Any other question? Yes.
So, Erik from Chalmers University. So, seems to be many things we would like to work on together. So, why not put together a funding program?
So from an NSF perspective, of course, that has to be discussed and proposed and internally that the money is committed. But if sometimes finding that commitment may be difficult because everyone wants some, part of that pie, that budget. Instead, what we have been doing with other countries is that leverage the existing programs and then issue a mechanism at NSF we call Dear Colleague Letter, just to announce to the community that, hey, if you want to submit a joint proposal to NSF under one of the participating programs, you can do so and just get your research funded through the existing programs. So this reduces to chasing additional funding from other sources and reduces the paperwork and all sort of administrative load for the program directors, and it has been very, very, very effective so far. So I think most of our discussions are centered around leveraging the existing programs, similar to like Convergence Accelerator. We are not really creating additional the funding opportunity, at least at NSF, but leveraging the existing opportunities, but also leveraging the potential synergy between researchers from both countries.
Yes, absolutely. I mean, that's along the lines also of how we are talking about this at Vinnova. So, I mean, but yes. As our relationship develops, we can come back with more details on how to proceed.
Can I ask a follow-up?
Sure.
Not as a panelist, as audience. So one program that I'm familiar with is the US-Finland program, and that's a partnership between NSF, Techis, and the Academy of Finland, right? So
Academy of Finland.
Similar structure in Sweden, where the proposals get judged completely by panels in the US, and then in that case, the Finnish agencies abide by that decision and fund the Finnish portion. Is that what you have in mind for some of these discussions?
That's what we're looking at, also similar, where we have, along those lines. But I don't want to preempt the final discussion there, but it's...
a lot of thinking goes into this, but something along those lines, or whatever works for both sides.
And for the applicants, I should say, not just for us, but for the applicants.
Communities.
Exactly.
NSF, we claim, we always say it's community-driven, so it has to be. If if the community doesn't send any proposals, then what's the point of creating that program? So, if you can come up with a program or form a partnership, if there's only one or two proposals, that program will not go anywhere. So we need a buy-in from the community. NSF, even our regular programs, is community-driven. Any type of new opportunity we want to create, we have to hear that from the community. any, right.
Hello, Syed Zedi from University of Leeds in UK. I just wanted to ask you that we have discussed so many different applications potentially of 6G and digital transformation in general. This also means that the innovation landscape itself will be quite complex. And when we're talking about translation, national or bilateral collaboration, how do you support that sort of mapping of different disciplines and complementary expertise, especially where you have a huge amount of SME stakeholders, startups created by universities, for example, for which the visibility in other countries is not that clear. We know the big players in the space, but how do you support those sort of smaller players to scale up and collaborate with other countries where the complementary expertise exists?
Maybe I can just
Sure.
comment on
Please.
one of the items in our MOU is really to also create these joint conferences and meetings and workshops where we can bring stakeholders together, and that's a way of actually getting, the high touch type of processes, which may later evolve into joint projects. So that's one thing, just creating a higher awareness of what's out there, what's possible, creating those links, because it's really at the end of the day, it's really the interpersonal relationship between the ones that are actually going to collaborate that makes a huge difference whether a project is successful or not. So that's one of the items that we propose, at least.
All right. Well, I'd like to thank all the panelists and audience for all the questions. Appreciate the opportunity and the invitation, and would like to end our panel here and get back to you. Thank you.
Thank you. Thank you very much. Thank you very much, Dr. Torlak, for excellent moderation of this panel. And it's my pleasure now to invite to the scene Markus Wallenberg, who is the chair of our academy and who will close this part of the symposium. The floor is yours.
Thank you. Well, thank you, Tuula. And it was very interesting to be here and listen to what was being discussed. I guess that we are lucky to have started, or not started, but having this cooperation between different countries in terms of doing research collaboration. And I think, with my experience, I think the US-Swedish collaboration has been extremely fruitful over the years, and I hope that will continue. The inter-academy collaboration is extremely important. I just see from my vantage point that the speed at which scientific development is now going, and we see the outcomes of and the combinations of AI, telecommunications, cyber, and I would guess also in the field of sustainability, there are still extremely big areas that we haven't really developed and to its full extent. So this research collaboration is going to be very, very important. I was actually a little bit surprised, and I don't know if it fits in or not, but we speak in the financial world a lot about cryptocurrencies. And I'm not saying that you should get into cryptocurrencies, but I wouldn't even recommend it. But I think that when we speak about security and the way of handling a lot of information in a safe way, I think the crypto technologies have actually a lot to offer that we don't think about on an everyday basis. Maybe that might be a part of it. But why are we doing this? Well, this may develop systems not only in the 5G and 6G area, but systems that can be used in affordable ways going forward. And if you look at the telecom market, I think that's been perhaps one of the big successes, is that you've really been able to get a global system going, affordable for billions of people to access it. And that has been a very, very fruitful and good development, I think, also in economic terms, not only for those participating in those industries. And that's why it's so incredibly important. I would also hope that you will touch upon the possibility to deepen the research collaboration by exchanging faculties and students between the countries and over the continents, because at the end of the day, to get a real win-win situation, and I think we heard that in the panel as well, to get a really good development, you need to have a win-win concept by people collaborating intensely in the research with each other. I think it's been proven time and time again, and therefore I think these exchange programs are extremely valuable. So I hope you're going to have a wonderful evening. I hope you're going to have a wonderful stay also tomorrow and a good session then as well. So thank you very much, and thanks for your invitation, Tuula. Good evening.
Thank you very much, Markus. And this is closing our session today. Now we are taking one stair up, and there will be some wine and mingle food. Thank you. So please, to the next floor.